Okay, G, we are going to do example number 1.3. Example number 1.3 says, consider the sketch for the voltage across the capacitor as shown in figure number 1.9. This is the sketch for the voltage across the capacitor, and you see the voltage across the capacitor is changing with respect to time. Initially, the voltage across the capacitor is increasing linearly with respect to time. Then this voltage is constant with respect to time, and finally this voltage decreases with respect to time. So this is the sketch for the voltage across the capacitor, and this is a time varying voltage. Sketch the current in the capacitor and power taken by the capacitor is a function of time. Capacitance of the capacitor is 10 farad. So we have been given the capacitance of the capacitor, which is 10 farad, and we have been given the sketch for the voltage across the capacitor, and with the help of this sketch we are going to sketch the current in the capacitor and the power taken by the capacitor as a function of time. We divide this graph into three regions. This is region number 1. You see, in region number 1 the time is changing from 0 to 1. This is region number 2, and in region number 2 the time is changing from 1 to 3. And then this is region number 4, where the time is changing from 3 to 4. So here is region number 1, and here is region number 2, and here is region number 3. So we divide the graph into three different regions. In region number 1 the time is changing from 0 to 1. In region number 2 the time is changing from 1 to 3. In region number 3 the time is changing from 3 to 4. So let us consider region number 1. If you look at the sketch in region number 1, there is a linear relationship between the voltage and time in region number 1. So we consider region number 1 where the time is changing from 0 to 1. In this particular region, the voltage across the capacitor is changing with respect to time, and it is changing with respect to time linearly. Okay, you see this is a straight line which passes through the origin, and we know that the equation for the straight line is given over here. The voltage across the capacitor will be equal to mt plus c, where m represents the slope of the straight line and c represents the y-intercept. Keep it in your mind that if the line passes through the origin, then c will be equal to 0. The y-intercept will be equal to 0 if the line passes through the origin. So c in this particular equation will be equal to 0. What we are going to do, we are going to find out the slope of this straight line in region number 1, which is represented by m. So let us calculate the slope of this straight line. Let me draw the straight line once again. We have time along the horizontal axis, and we have voltage across the capacitor along vertical axis. In region number 1, we have got a straight line which passes through the origin. You see the time is 1 over here and the voltage is 2 volt over here. So if I consider this end of the straight line, I have 0, 0 over here. This is 0, 0. So we have 0, 0. And if we consider this end of the line, we have 2, 1 over here. Okay. So we want to calculate the slope of this line, and the slope of this line, which is represented by m, will be equal to v2 minus v1 divided by t2 minus t1. This will be the slope of this line, where v2 is 2 volt. V2 is 2 volt. V1 is 0 volt. So V2 minus 1 will be equal to 2, and T2 is 1 while T1 is 0. So T2 minus T1 will be equal to 1 minus 0, which is 1. Let me write it down in this form. We have 2 minus 0 divided by 1 minus 0, and the slope of this line is 2. So we have calculated the slope of this straight line, which is 2. Y-intercept is 0. So the equation for this straight line is 2t. You see there is a linear relationship between the voltage across the capacitor and time. So this is the equation for the voltage in region number 1. This equation is valid in region number 1 only, where the time is changing from 0 to 1 second. This equation is not valid in region number 2. This equation is not valid in region number 3. So let us consider region number 2, where the time is changing from 1 to 3 seconds. So if you consider the voltage across the capacitor in region number 2, you see this voltage is constant with respect to time. This is the voltage in region number 2, which is constant, which is 2 volt. So the voltage across the capacitor in region number 2 is constant with respect to time. The voltage across the capacitor is 2 volt. So we have calculated the voltage in region number 2, which is 2 volt. Now we consider region number 3. We consider region number 3, where the time is changing from 3 to 4. And you see in region number 3, let me consider the line end region number 3. We have got time along the horizontal axis, voltage across the capacitor along vertical axis, and this is the relationship between the voltage and time in region number 3. You see the time is 2 over here. No, it's 3 over here, okay? The time is 3 over here. The time is 3 over here, and the voltage is 2 volt at this particular point. So you see, we have got a straight line which does not pass through the origin in region number 3. So this is the equation of a straight line which does not pass through the origin. The equation of the straight line which does not pass through the origin will be equal to mt plus c, where m is known as the slope of the straight line and c is known as y-intercept. So we will have to calculate, you see, the slope of this line as well as the the y-intercept, which is represented by t. So let me consider the line once again. We consider the straight line in region number 3 once again. We have got the time over here and we have got the voltage across the capacitor over here. And here is the straight line in region number 3. So if I consider this end of the straight line, the time is 3 seconds over here while the voltage is 2 volt. If I consider this end of the line, the time is 4 and the voltage is 0. Okay, so we can calculate the slope of this line. The slope of this line, which is represented by m, will be equal to v2 minus v1 divided by t2 minus t1. This will be the slope of this line, where v2 is 0 and v1 is 2. So we have 0 minus 2, which is 2 volt, minus 2 volts. And t2 is 4 seconds and t1 is 3 seconds. So 4 minus 3 is 1. And the slope of this line is minus 2. Okay. So the equation of this line will be minus 2t. We have calculated the slope now, which is minus 2, and we need to calculate, you see, c. So now we need to calculate c, and in order to calculate c, you see, this line is consist of points, and all the points will satisfy this particular equation. This is the equation of this particular line. So all the points on the straight line will satisfy this particular equation. I'm talking about this equation. So let us put this particular point in the line where the time is 4 and the voltage is 0. We put 4, 0 in this particular point. So the voltage is 0 and the time is 4. So we have minus 2 into 4 plus c. So c will be equal to 8. So over here c comes out to be 8. So the equation of this line will be minus 2t plus 8. So we have calculated the slope of the straight line in region number 3, which is minus 2, and the y-intercept is 8. So the equation for the voltage across the capacitor in this particular region is minus 2t plus 8. This is the instantaneous equation for the voltage across the capacitor, and this is the instantaneous expression for the voltage across the capacitor. So we have calculated the voltage in region number 1. The voltage in region number 1 The voltage in region number 1 is 2t. So there is a linear relationship between the voltage and time in region number 1. The voltage in region number 2 is 2 volt. You see, this voltage is constant in the second region, which is 2 volt. Then we consider the voltage in region number 3. So the voltage in the region number 3 is minus 2t, where minus 2 is the slope of this line, and plus 8, where 8 is the y-intercept. So we have derived these three equations from the sketch for the voltage across the capacitor. Now we are going to calculate the current in region number 1, the current in region number 2, and the current in region number 3. Once we derive the equation for the current in all these three regions, then we will sketch the current as a function of time. So we are going to calculate the current in region number 1. Let us consider region number 1, where the time is changing from 0 to 1. So we consider region number 1, where the time is changing from 0 to 1. You see, the voltage in region number 1 is known. The equation for the voltage across the capacitor in region number 1 is known, which is Vc is equal to 2t. We know how to calculate the current in the capacitor. So we can calculate the current in the capacitor with the help of this equation. The current in the capacitor will be equal to C into dVc by dt. The capacitance of the capacitor is 10 farad. So we differentiate this voltage with respect to time and we multiply it by t. So the current in region number 1 is 20 ampere. The current in region number 1 is constant, which is 20 ampere. You see, this current is constant in region number 1. These equations are valid in region number 1 only. We consider region number 2, and in region number 2, the time is changing from 1 to 3. The voltage across the capacitor in region number 1 is constant. So the voltage across the capacitor and region number 1 is constant, which is 2 volt. We calculate the current with the help of this derivative. The current in region number 2 will be equal to C dVc by dt. So the derivative of the constant voltage is 0. So there will be 0 ampere in the capacitor in region number 2. You see, the voltage across the capacitor in this region is constant. When you differentiate the constant voltage with respect to time, you obtain 0. So this is the current in region number 2. Now let us calculate region number 3. Let us consider region number 3. So we consider region number 3. Here is region number 3, where the time is changing from 3 to 4 seconds. This is the equation for the voltage across the capacitor in region number 3. The voltage across the capacitor in region number 3 is minus 2t plus 8. We differentiate this voltage with respect to time and then we multiply it by C. So the current, which is equal to C dVc by dt, will be equal to minus 20 ampere. So the current in region number 3 is constant as well. We are going to sketch the current with respect to time. You see, in region number 1, the current is constant. And how much is the current in region number 1? The current in region number 1 is constant, which is 20 ampere. The current in region number 2 is constant as well, but this current is 0 ampere. And then the current in region number 3 is constant, which is minus 20 ampere. So this is the current in the capacitor. This minus sign indicates that the current in the capacitor in this region will be in the opposite direction. So we are going to sketch the current now. We take the time along the horizontal axis and the current along the vertical axis. You see here is region number 1. The current in region number 1 is constant, which is 20 ampere. Here is region number 2 where the current is 0, and then here is region number 3 where the current is minus 20 ampere. So this is the sketch for the current in the capacitor is a function of time. Now we are going to sketch the power as a function of time. So we consider region number 1, and you see in region number 1 the time is changing from 0 to 1. The voltage across the capacitor in region number 1 is 2T, while the current in the capacitor in region number 1 is 20 ampere. So the voltage across the capacitor in region number 1 is known. The current in the capacitor in region number 1 is known. Definitely the power will be equal to 40 watt. The power will be equal to 40 T watts. The product of the voltage and current is known as 40 T. You see, if you look at this relationship, there is a linear relationship between the power and time in region number 1. So definitely you guys will get a straight line passing through the origin in region number 1. This is one way to sketch the power. There is another way to sketch, you see, this particular power. The power is changing with respect to time, which is equal to 40T. This equation is valid in region number 1 only, where the time is changing from 0 to 1. Okay. So let us calculate the power at time t is equal to 0. At time t is equal to 0, the power will be equal to 40 into 0, which is 0 watt. Then we calculate the power at time t is equal to 0.5. So we have 40 into 0.5, which is equal to 20 watt. And then we calculate the power at time t is equal to 1. So we have 40 and the time is 1. So we have 40 watt. So you guys can sketch these points in region number 1, and you guys will get a straight line, and this line will pass through the origin, right? So this is another way to sketch the power as a function of time. Now we calculate the power in region number 2. You see, in this region the time is changing from 1 to 3. The voltage across the capacitor is constant, which is 2 volt. There is no current in the capacitor in region number 2, which is 0. So definitely the power taken by the capacitor in region number 2 will be 0. In this region, the capacitor does not take any power from the voltage source, so we obtain 0 watt. Now we consider region number 3. In region number 3, the time is changing from 3 to 4. The voltage across the capacitor is known in region number 3, which is minus 2t plus 8 volt. The current is known in region number 3, which is minus 20 ampere. There is a constant current in the capacitor in region number 3. this minus sign indicates that the current in the capacitor will be in the opposite direction. So we calculate the power taken by the capacitor will be equal to Vc into I, where voltage across the capacitor is minus 2t plus 8 and the current in the capacitor is minus 20. If we simplify this particular equation, we get 40t minus 160 watt. This will be the instantaneous equation for the power in region number 3. While the time is changing from the time is changing from 3 to 4 in region number 3. So you guys want to sketch this particular power as a function of time. So what you guys can do, you guys can find out the values of the power at different time, at different instants, and then you guys can sketch this power as a function of time. You see, just calculate the power at time t is equal to 3. Then calculate this power at time t is equal to 3.5. Then calculate this power at time t is equal to 4. So if you do that, you guys will get different points and then you guys can sketch it. So if we calculate this power at time t is equal to 3, we will get minus 40 watt. If we calculate it at time t is equal to 3.5, we will get minus 20 watt. And if we calculate it at time t is equal to 4, we will get 0 watt. You guys can sketch these 3 points with respect to time, and you guys will get, you see, the sketch for the power is a function of time. So let me consider the equation for the power in 3 regions. So the equation for the power in region number 3 is 40t. This is the equation for the power in region number 1. The equation for the power in region number 2 is 0 watt, because the current is 0. So the capacitor will not take any power in region number 2. Then we have the power taken by the capacitor in region number 3, which is equal to 100 which is equal to 40t minus 160, right? So this is the equation for the power in region number 1. This is the equation for the power in region number 2, and this is the equation for the power in region number 3. You guys can find out, you see, the power at different values of time, and then you guys can sketch it. Anyhow, we sketch this power. So you see, the power is changing from 0 to 40 watts in region number 1. Then this power is 0 in region number 2. And if you consider the power in region number 3, it is changing from minus 40 to 0 watt in region number 3. So this is how we sketch the power as a function of time. We do example number 1.4. In example number 1.4, consider the sketch for the current in an inductor of 10 Henry as shown in this particular figure. So you see, this is the sketch for the time varying current in an inductor of 10 Henry. So you see, initially the current is increasing from 0 to 2 ampere, and then this current is decreasing from 2 to 0 ampere. So basically there is an inductor of 10 Henry, and the sketch for the current in this inductor is given over here. The inductance of this passive circuit element is known, which is 10 Henry. So on the basis of the sketch and the inductance of this passive circuit element, we are going to sketch the voltage across the inductor, and the power taken by the inductor is a function of time. The inductance of the passive circuit element is 10 Henry. So what we do, once again, we divide this sketch into two regions. We divide this sketch into two regions. This is region number 1. Okay, in region number 1, this is region number 1. In region number 1, the time is changing from 0 to 1, and the current is changing from 0 to 2 ampere. So this is your region number 1. Now we consider region number 2 over here. This is region number 2. So in region number 2, the current is changing from 2 to 0 ampere. So this is region number 2, and here is region number 1. So we divide the sketch into two regions. Region number 1, where the time is changing from 0 to 1, and region number 2, where the time is changing from 1 to 2. Okay, so let us consider region number 1. In region number 1, the time is changing from 0 to 1, and the current is changing from 0 to 2 ampere. The current is changing from 0 to 2 ampere. So in this region, we have a straight line which is passing through the origin of these two coordinates. So the equation of the straight line which passes through the origin will be equal to mt plus c, where m is known as the slope of this line, c is known as y-intercept. Whenever the straight line passes through the origin, c will be equal to 0. So c in this particular case will be equal to 0. Why? Because this line is passing through the origin. What we need to do, we need to calculate the slope of this line. So let us calculate the slope of this particular line. So we calculate the slope of this line. We consider region number 1, and we consider the slope in region number 1. We have got the current over here, and we have got a straight line in region number 1. So we consider this end of the line where the time is 0 and the current is 0 as well. And then we consider this end of the line where the time is 1 and the current is 2. So now we can calculate, you see, the slope of this particular line. The slope of this particular line will be equal to I2 minus I1. So I2 is 2 and I1 is 0. So we have 2 minus 0 divided by T2 minus T1. T2 is 1 and T1 is 0. So we have 1 minus 0 and the slope of this line is 0. So the slope of this line is, the slope of this line is not 0, it is 2. This is just a slip of tongue. So the slope of this line is 2. Now as the line is passing through the origin of these two coordinates, so the y-intercept will be equal to 0. And definitely the equation for the current in region number 1 will be equal to 2t. This is the instantaneous equation for the current in region number 1. This is how we calculate the current in region number 1. So we have calculated the slope of the straight line in region number 1. So the slope of the straight line in region number 1 is 2. This y-intercept is 0. So this is the instantaneous equation for the current in region number 1. Now we consider region number 2 where the time is changing from 1 to 2. So in region number 2, the current is decreasing from 2 to 0. You see, the current is decreasing from 2 to 0. We have got time over here and we have got the current over here. So you see, at this particular point the current is 2 ampere, and at this particular point let me consider the time. Okay, the time is 2. The time is 2 over here, right? So the time is 2 at this particular point. Now this is a straight line which does not pass through the origin, and the equation of the straight line which does not pass through the origin is given over here, which is mt plus c, where m is known as the slope of the line and c is known as y-intercept. So we need to calculate the slope of this line as well as y-intercept. The slope of this line comes out to be minus 2 and y-intercept comes out to be 4. Anyhow, let us calculate the slope of this line on the next slide. So let me consider the current in region number 2. This is how the current varies in region number 2. So we consider this end of the line where the time is where the time is 1. Let me erase it. We consider this end of the line where the time is 1 and the current is 2. Then we consider this end of the line where the time is 2 and the current is 0. So we calculate the slope. The slope of this line will be equal to I2 minus I1. So I2 is 2 and I1 is 0. So we have 2 minus 0, I2 minus I1 by T2 minus T1. So T2 is 2, T1 is 1. So we have 2 minus 1. Okay, I have done a mistake. Let me erase the slope over here. So I have I2 minus I1. So I2 is 0 and I1 is 2. So I have 0 minus 2. Sorry, I wrote 2 minus 0. And then I have T2 minus T1, which is 2 minus 1. So the slope of this line is minus 2. So the equation for the line will be equal to minus 2t plus c. This is the equation of this straight line, and this any point on this straight line will satisfy this equation. So let us put this particular point over here where the current is 0 and the time is 4. So C will be equal to 4. You guys can put any point of the line in this particular equation and you guys can find out this y-intercept C. So the equation for this line in region number 2 is minus 2t plus 4. This is the instantaneous equation for the line in region number 2, and this is the instantaneous equation for the line in region number 1. So we know the equation for the current in region number 1 and the equation for the current in region number 2. Now we can calculate the voltage across the inductor and the voltage across the inductor in region number 1 as well as 2. So we are going to calculate the voltage now. We consider region number 1. The time is changing from 0 to 1. The current in region number 1 is 2t. We calculate the voltage across the inductor with the help of this particular equation. The voltage across the inductor will be equal to L di by dt. So the inductance is 10, the current is 2t. So the voltage across the inductor in region number 1 is constant, which is 20 volt. Then we consider region number 2. In region number 2, the time is changing from 1 to 2. The current is changing with respect to time in region number 2, where the current is minus 2t plus 4. So we calculate the voltage across the inductor in region number 2, which is L di by dt. If we calculate this voltage in region number 2, this voltage is constant, which is minus 20 volt. So the voltage in region number 2 is constant. So what we do, we sketch the voltage with respect to time. So we take the time along the horizontal axis, the voltage across the inductor along vertical axis. You see the voltage across the inductor is constant in region number 1, which is 20 volt, and the voltage across the inductor is constant in region number 2 as well, which is minus 20 volt. So this is the sketch for the voltage across the inductor in region number 1 as well as region number 2. Now we calculate the power. So we will calculate the power in region number 1. Then we will calculate the power in region number 2. And finally, we will sketch this power in region number 1 as well as region number 2. So the current through this inductor is changing with respect to time in region number 1, and here is the instantaneous equation for the current in region number 1. The voltage across the inductor is constant in region number 1, which is 20 volt. So the power taken by the inductor in region number 1 will be equal to 40 t volt. And you see there is a linear relationship between the power and time. If there is a linear relationship between the power and time, you guys will get a straight line passing through the origin in region number 1. Anyhow, so we consider region number 1 where the time is changing from 0 to 1, and the power taken by the inductor in region number 1 is 40 t watt. So the power taken by the inductor at time t is equal to 0 will be 0 watt. The power taken by the inductor at time t is equal to 0.5 will be 20 volt, and the power taken by the inductor at time t is equal to 1 will be 40 watt. So you guys have the power at time t is equal to 0, which is 0. You guys have got the power at time t is equal to 0.5, which is 20, and you guys have got power at time t is equal to 1, which is 40. You guys can sketch these 3 points in region number 1. You guys will get a straight line passing through the origin. Anyhow, let us calculate region number 2. We consider the time in region number 2, which is changing from 1 to 2. We consider the time varying current in region number 2. The equation for the time varying current in region number 2 is minus 2t plus 4. The voltage across the inductor in region number 2 is constant, which is minus 20 volt. So the power taken by the inductor in region number 2 will be equal to 40t minus 80 watt. This is the instantaneous equation for the power in region number 2. Let me consider this equation. This is the equation for the power 40t minus 80. This is the equation for the power in region number 2, and in region number 2 the time is changing from 1 to 2. So let us calculate this power at time t is equal to 1. At time t is equal to 1, we have 40 into 1 minus 80, so we get minus 40 watt. Then we calculate this power at time t is equal to 1.5. So at time t is equal to 1.5, this power will be minus 20 watt. And then we calculate this power at time t is equal to 2. So at time t is equal to 2, we have 80 minus 80, and this power will be 0. So this is the power at time t is equal to 1. This is the power at time t is equal to 1.5. This is the power at time t is equal to 2. You guys can sketch, you see, this power with respect to time. You guys can sketch these values with respect to time, and you guys will get the graph for the power. So we sketch the power as a function of time over here. You see, this is the sketch for the power. In region number 1, the power is changing from 0 to 40 volt, and this is the sketch for the power in region number 2. In region number 2, the power is changing from minus 40 watt to 0. Thank you so much.